I just did the link.
That's Kimchi, it sounds like, with the semi-board response there. So anybody like find me by looking up your humble servant or anything, or did you just click the link?
I used the link.
Okay. Yeah. All right. Well, it was kind of cool. I got to like hook up the link, and some of my Chem 110s were able to find me just by searching that in the Zoom. And it turns out that every time I generate a link, it gives me the same link. So it wasn't doing a randomized link, and that's when I found out I could just make my own little room, my own little corner of the universe. Okay, so let's do the one more of the titration problems. Let's say we want to make. Oh, do we have any questions before I start? I'm sorry. That was kind of not cool of me. Hearing none, let's do one more titration one and then move to pH controlled solubility. Let's see. How much? (0.4 molar sodium hydroxide do we need to add to 100 mils of 1 molar phosphoric acid to make a buffer of pH 7. So I'll remind us that we have H3PO4 goes back and forth to make H plus, and H2PO4 minus, and this has a pKa equal to 2.12. We have H2PO4 minus back and forth to make H plus and HPO4 2 minus. And this has a pKa equal to 7.21. And finally, our HPO4 2 minus goes back and forth to make H plus and PO4 3 minus. That has a pKa equal to 12.67. Hopefully by now, obvious, the answer is obvious, but there is a reason why I'm doing this. If we're doing a 7, we might want to get to that 7.21. Does anyone see a potential problem here, Dallas? Hearing nothing from Dallas, who doesn't see my potential pitfall. I'm going to say potential problem. Where we want to be is where? Where we want to be is in region 2. Okay, so this, I mean, it's a problem, but it's not. I mean, we did this titration with a monoprotic last time, and it was merely just add this much stuff in. It really is going to be exactly the same. When I say potential problem, it's really not a problem. So it's not really a problem. Not really a problem. And that is because all we really have to do is figure out where we would need to be in region 2 to begin with, and just dump in all the excess that we need to just get to region 2 in the first place. Okay, so if we find out that we have to only add 25 mils into region 2, but it took 100 mils to get to region 2, we'll dump in 125 mils. It's really no more complicated than that. But it's worthwhile to point out that this is the case. It's not really a problem. Just determine how many mils we need if we were in region 2. And add enough mils to get to region 2 in the first place. So let's get into region 2, then get through region 1. Get into region 2, get through region 1. So to get to region 2, we have pH equals pKa plus log of x over A minus x. So we need A, so we need the A in moles. So we said that was a 1 molar solution, so 1 mole of H3PO4 per liter of H3PO4, and we had 100 mils, so 0.1 liters of that solution. And that gives us 0.1 moles of the acid. And that's our A. At this point, we can plug and chug. We knew that, that our pH was supposed to be 7.00. Our pKa was 7.21. Plus log of x over 0.1 minus x. So all of this Henderson-Hasselbalch stuff we're doing is no different than what we were doing when we just built the titration curves. We're just going to back out and solve for one of the variables, not a drama. We'll go ahead and just finish up that math. So we have 7.00 minus 7.21. Equals log of x over 0.1 minus x. We'll go ahead and 10 to the of both sides. And we'll end up with we'll end up with 0.6166 is equal to x over 0.1 minus x. Not really worrying about it. We're just going to say solve. X equals 0.0381 moles of base. Remember, this is in moles. So now we have to figure out the actual volume of that. So the volume of the base, this is going to be 0.0381 moles of sodium hydroxide. And we have moles of sodium hydroxide per 1,000 mils. of sodium hydroxide. And that'll be 95.35 mils into region 2.
I'm getting 95.25.
25?
Yeah.
Well, in the past I had a 2, and for some reason I scribbled a 3. If it's a 2, that's fine. Does anyone else confirm before I solve that or do that? Because clearly I used to have a 2, then someone gave me a 3, and so I scribbled over a 3, which means some student somewhere is lying to me.
I got 0.25 also.
0.25.
Roger that, 2.5. Let me make a change on my notes. So now you can blame a previous class for saying that I was wrong. Okay, so that is the 95.25 into region 2. We just have to get there in the first place. So now get to region 2 in the first place. And how do we get to region 2 in the first place? What does it mean?
Add enough base so that it neutralizes the first H plus in each of the molecules.
And how do we get that?
M1V1.
That is correct. So use M1V1 equals M2V2 to get endpoint volumes, just like normal. So it is, we had our 1 molar solution, or 0.4 molar solution, and we want our V2. Our V2 is going to be 250 milliliters. So this gets us through region 1. Therefore, 250 mils plus 95.25 equals 345.25 mils to get pH 7 solution. Now I had in there that we were going to go ahead and go into the third section, but I have a feeling that you guys are okay with doing this. If we had to go into region 3 to make a buffer of 10, then figure out how much we were in region 3, and that should be kind of a no-brainer. Preguntas, mis estudiantes? Dallas, go ahead and chime in and say no so I can move on.
No.
I have a question. Would you have been able to do M1V1 before you did pH equals pK plus log of?
Yeah, you could figure out the endpoint if you knew that you were going to go into another region. You could go ahead and do M1V1 and have that volume sitting off to the side, waiting to be dumped in at the end of all things. I just decided to figure out how much I need into region 2 to begin with, and then, oh yeah, I need to get through region 1. Let's just figure it out. It really doesn't matter since it's addition. Remember, no matter which way you add, the numbers will work out.
Okay.
That sounded like Chef. Was that you, Chef?
Yeah, it just makes more sense for me to know that I'm going through region 1 first and then into region 2, but.
That's fine. That's totally the way to do it. I mean, it's the wrong way to do it. No, I'm kidding. I'm kidding, Chef. No, actually, you're not the first person to say, why don't I get through region 1 first? why don't I do the M1V1, hold on to that volume, and then add in the region 2 volume? That is absolutely a good way of going about it.
Cool.
You know what I just realized to fix my tower to make me have good speeds and stop having this little screen that flashes up says, my internet is unstable. I hope they actually come after lecture. Huh. That would suck if they like took down all my internet in the middle of all this. We'll see. Is somebody screaming at me?
It's Kimchi.
Hi, Kimchi.
Hi.
Hi.
You just mentioned the if you were doing in region 3, so to get through region 2, would it just be like the same amount?
It'd be 500 now to get through region 1 and region 2.
Yeah. Okay.
Yeah. Okay. New topic. Yay! Last topic before we take our exam on the Tuesday we come back from break. Wow, no one freaked out?
Sorry, I was unmuted.
No.
It is what it is.
Yeah, I either wanted to hear screams or a pin drop, and I got the pin drop. That was interesting. All right. So
Do we really?
pH, controlled solubility. pH controlled solubility. Remember KSP, right? This was a solid breaking up. This meant solubility product. How soluble is the product you made? Solubility product. That's what we're going to be investigating now. pH controlled solubility is one of those really interesting things that you don't know controls a lot of your life. It turns out that since everything has its own solubility, there are a few things out there that can be controlled using the pH of the solution, and changing the H plus or OH concentration will make certain, especially transition metals, certain transition metals fall out of solution before others. And it's really useful for removing some of the heavy metals out of solutions for wastewater treatment and the like. So when I first saw this, I was like, well, this is kind of a niche thing. And then I realized all of the applications that actually rely on this. So it got me really excited about it when I realized just that it has a real world application. I just want to point out here, when we are writing these KSPs, so recall how to write KSPs, because we haven't done this in a few weeks. So let's say that I have silver chloride, that's a solid, back and forth to make its silver ions and its chloride ions. This is standard. We did a whole lab on this. If I wrote the KSP for this, what would that look like? Lion Lee, are you here? Not Lion Lee. Let's see who's here. Show, where's all my participants? There we are. Who's around here? Oh, Alexia, you're here. Do you remember how to write them?
It's not reactants over products, is it?
It's products over
Or
reactants.
products, okay.
So tell me.
Ag plus Cl minus
I'm Cl minus.
over AgCl.
Now, Kimchi's shaking her head. I can see it. Why are you shaking your head, Kimchi?
I'm not sure.
How do you get the concentration of a solid?
Is Ben in here?
Yeah, I'm here.
That's correct. Remember the old school, right? The solid goes away. We don't use the solid in there because what's the concentration of a solid in a solid? It's Doesn't make sense. So remember, we don't do that. Instead, we just write it as KSP is just equal to the things we're looking for, and that is the stuff floating around in solution. This one actually happens to have a 1.8 times 10 to the minus 10 for its KSP. You wouldn't know that. I would have to give that to you. Fret not. All right. So let's see. What if we had aluminum hydroxide? So AlOH3 solid. This goes back and forth to make aluminum with a 3+ aqueous and 3 hydroxides, of course, aqueous. I'm going to give this one to Chad Robbins because that's who shows up on my chat window right now. Chad Robbins. Let's see if you remember how this is done. I know it's been a way back machine. KSP is equal to what?
Well, it's supposed to be the reactants in, I'm sorry, the products in solution, right? So they have concentration L 3+, and OH, concentration OH minus.
Ira. Is he forgetting something?
Yes, I'm sure I am. Wait.
Yeah, the OH minus should be cubed.
Oh, yes, thank you.
That is correct.
Yeah.
Yeah, no, and keep in mind, you know, we haven't done this for a while, so I expect us to be like, wait, what is this guy asking? Because we haven't talked about it in a long time, right? So let me just be very clear here. That made 3 OHs, which means that's going to be cubed. And we're going to show you something even cooler about that later. All right, so not to put too fine a point on it, I'm going to give this to the great gherkin. We have calcium phosphate, Ca3, parentheses, PO4, 2. That's a solid. We're going to go back and forth to make 3 calcium 2 pluses, aqueous, and 2 phosphates, aqueous. I don't know how you became the great gherkin, but you're the great gherkin now. Caroline, for the win. Tell me how to do it.
Okay, so you're gonna have Ca2 plus cubed times PO43 minus squared.
That is correct. And I'm gonna go ahead and change those. Hey, Boudica, is there a fast way for me to change them or do I have to circle them all?
I think you just have to circle them.
Oh, man. Oops. Wow. So I'm just going to do this for emphasis, just to remind us that that's why we're doing this. Oops. All right. So just a quick reminder there. Oh, I did want to put the KSPs for that. The aluminum hydroxide, just for kicks. This one happens to be 1.6 times 10 to the negative 33. And our good old-fashioned bones are 8.1 times 10 to the negative 13. So one of the things I want to point out is each one of these has their own KSP. They will vary. Some things are more soluble than others. Let's talk about that solubility one more time. What does it mean to be soluble? And is anything really insoluble? So let's do our cool little note one more time. Soluble is a 0.1 molar solution. So that means on the other side, your concentration of your ions will be 0.1 or more. So your ion concentration your ion concentration will be 0.1 molar or greater. Okay. I love this. Did he start recording this? Oh yes, never mind kimchi.
I don't remember.
Does that mean, are you asking that so that you can ditch out and go take a nap?
No.
Did anyone else catch the sheepish laughter on the back end of like I caught her with her hand in the cookie jar? Hey, Ben and Garrett, are you guys feeling better yet or what?
Yeah, I'm cool.
I don't think Garrett's here.
Uh-oh, somebody better check on him.
Probably playing Animal Crossing.
Oh yeah, probably playing Animal Crossing. Well, he was doing that during lecture last time anyway. All right, let's check this out. The world's most insoluble compound. And go ahead, Dallas, look it up and make sure that I'm wrong. Oh man, I can't. Ah, you're right at the edge. There we go. The world's most insoluble compound. This is going to be mercury sulfide. This is going to go back and forth to make the mercury 2 ion and sulfide ion. Now, if we were to write the KSP for this, the KSP would be equal to the concentration of mercury 2 plus and the concentration of sulfide. This happens to have a KSP with a wonderful, glorious value. In fact, this is how awesome it is, 6.38. Oh, if we can write that a little nicer, 6.38 times 10 to the negative. Let's see, who's gonna take a stab? Lion Lee, how insoluble is this? 10 to the negative what? All right, hearing Lion Lee not participating, Meng, take a stab. How tiny do you think this is gonna be, or how big do you think that negative number might be?
18.
What do you mean, no, just say a number. I mean, if you look back up here, what do we have? We have negative 10s, negative 13s, negative 33s. Take a stab. How insoluble can this be?
45.
Close, actually. 53.
Damn.
So check this out. Let's set up a little ice table for this. Let's do HGS, Hg2 plus, and S2 minus.
Red or black?
What do you mean red or black?
Mercury sulfide red or mercury sulfide black? Apparently they have different.
Which one is the one I'm looking at then?
I don't know because they both have 2. It's 2 times 10 to the negative 53 and 2 times 10 to the negative 54.
Yeah, so that's probably why this is an agglomeration of both of them, maybe somewhere in the middle.
Right.
So yeah, but I wasn't wrong. We're stupid and soluble. I hadn't actually looked up the difference on those. I don't remember which one I looked up when I did this, to be quite honest. All right, so let's take a look at this. If we look at our initial concentrations, hopefully clearly you see that we don't care about the mercury sulfide, because what does that even mean? Let's solve this like we normally would. We assume we have nothing. And then, of course, as it decides to reach an equilibrium, we will add the x's and go from there. And of course, this means that we have x squared is equal to, well, do I need to point that out, that I'm just going to put the x's up in there? Okay. So I'm just going to solve that. X squared is equal to 6.38 times 10 to the negative 53, which means that x is equal to
7.99 times 10 to the negative 27.
So that is the concentration of any mercury floating around and any sulfide floating around. But normally, we just care about the metal, normally. So I love this calculation. And that is because what I'm going to ask you is, if I put some mercury sulfide into a liter of water, how much actually goes into solution? How much breaks apart? How much dissolves? So if I put a chunk of mercury sulfide, mercury 2 sulfide, into 1 liter of water, how much dissolves? How much actually dissolves? Well, we know that we'd have 7.99 times 10. Oh, I can write that a little better. 7.99 times 10 to the negative 27 moles per liter. That was a concentration. And we're going to use something that I told you way back in Chem 110 that we'll never use again except for once. In Chem 121, man, can you remember what that thing was that we'll never use except for once in Chem 121?
No,
Say it.
I don't remember.
The most useful, useless number?
Oh, Avogadro's number.
That's right. So we know that 1 mole is equal to 6.022 times 10 to the 23rd.
Oh, 23rd.
Uh-huh. So if you do that, this is 4.81 times 10 to the negative 3 atoms in 1 liter. For those who need that visually, so check it out. You need 1,000 liters to get 4 atoms to dissolve. That's kind of cool. Which, by the way, is why whenever anyone breaks some sort of thermometer that has mercury, for the very few that we have left, when somebody does that, the first thing I do is I go for this sulfur. And I toss that sulfur onto the mercury to try to bind up the mercury and make it a solid. Because guess what? It's not going to come out as solid.
It's not going anywhere.
It's not going anywhere, right? You have to do special stuff to take care of it, to get it back out if you want it. All right, so let's go back to our former examples. Let's go back to those silver chlorides, the aluminum hydroxides, and the calcium phosphates. I want to look at their solubilities. Let us get the solubility. of our first 3 examples. The first one we had was the silver chloride. We had AgCl going apart to give us Ag pluses and Cl minuses. If we were to go ahead and I'll go ahead and put the KSP. KSP equals 1.8 times 10 to the minus 10. If we were to do an ice table, can we agree that we're going to start out with the AgCls doing nothing? Well, let me just go ahead and do it. And then I'll stop doing it here at the end. We can agree that nothing happens with our AgCls. We can agree that we start out with nothing. We're going to add x's. And at the end, we have x over x. What I'm going to emphasize here is that we can skip all of this initial part because we know that the solid won't do anything. We're always going to be adding the requisite number of ions and then solving this. So our KSP is equal to the concentration of Ag plus times the concentration of Cl minus. We know that's going to be x times x is equal to the KSP, which is 1.8 times 10 to the minus 10.
Yes.
All right, who's that sheepish? That sounds like chef or kimchi when it's that sheepish.
It's kimchi.
Hi, kimchi.
Hi. So the AgCl, it's not doing nothing, but we just don't really care about it.
Because what is the concentration of a solid?
Oh, it's just okay. Sorry.
Right.
Right.
So when you're asking that, it's like you could give it whatever initial concentration it is, but what does that even mean? How much silver chloride is in silver chloride? Wait, what? We're always talking about a solute dissolved in a solvent to get a solubility.
Mm-hmm.
It makes no sense to talk about a pure liquid. What's the concentration of water in water? You can talk about the concentration of anything else in water.
Mm-hmm.
But when you talk about the concentration of a solid chunk of something sitting at the bottom of the lake, what is that a concentration of? That makes no sense. You can get the concentration of the things that it gives off, those ions.
Right.
But what are the concentrations of rocks in a lake? But you can get the mineral content, which are the ions that the rocks will give off.
Uh-huh.
Okay.
Is there like a final concentration of AgCl in the water or whatever?
Yes, that's what we're going to do right now.
Oh, okay.
On that note, we always assume that we're doing this in water.
Yes.
What happens if you do it in a different liquid?
It would have a different solubility product. So it's not that the process changes, it's just that your value might change. For instance, when I do the density demo for Chem 110, which you didn't see, but for those of you who've been with me a while, if you guys remember the water, the oil, the alcohol, and I made the red, white, and blue. When I dissolved the blue ink into water, it dropped in, not a problem, dissolved awesomely. When I went the red ink into the alcohol, it took a little bit of coaxing. And if you think about it, that makes a little sense. Your dye is supposed to be, quote, water soluble, which means it's a polar molecule. Duh, polar likes polar. Water will dissolve that. Now, alcohol is polar, but is it as polar as water? No. And so its solubility, ability to dissolve, was less. It didn't mean that I couldn't, it just took a little more coaxing to get it to go do its thing. So the process here, Dallas, is exactly the same. It's just that your value might not be 1.8 to the negative 10. It might be something different, maybe to the negative 13 or something. It could be even less. Maybe you have something that actually wants to dissolve it. At the end of the day, the X is going to be, I believe, 1.34 times 10 to the negative 5. And at this point, if either Ariana or Ferris were here, let's see, is Ferris here? Oh, no Ferris and no Ariana. So my stunt double for that is going to be Rio. Rio, what is X? Hearing no rivers to lull us to sleep. Loban.
The X is the ending amount, right? The ending concentration.
So keep in mind when I say what is X,
The amount of Ag and Cl.
yes, it's actually the concentration of both of those. Okay.
Maybe you should write and so that doesn't seem like.
Oh, yes. Oh, my apologies. Whoever just caught me on that. Was that you, Kimchi?
Yeah.
Or Kimchi's really good at pointing out my mistakes. All right. Who wants to do the next one? That aluminum hydroxide.
I can do it.
Of course you can, Dallas. At the end of everything, at the equilibrium, what are going to be my X's?
It's going to be the concentration of Al3 plus, and it's going to be what?
Go ahead.
So your X is going to be concentration of your Al3 plus, and then it's going to be 1/3 your concentration of OH minus.
OH is going to be 3 times aluminum. So let me just show you this real quick again, because I think it's useful. If we set up our ice table like we normally would, what does our aluminum go up by? It goes up by X.
3x.
But Tanaris, what does OH do?
3.
It goes up by 3.
That's right. So at the end, we have X and 3X, okay? That's what we're looking at. So when we set up our KSP, check it out. And this is where Dallas is sort of going here. KSP is equal to the concentration of Al3 plus. And he said the OH minus, say it, Dallas.
Cubed.
Cubed.
Yeah, sorry. Thing was off.
No, you're fine. All right. So I'm going to go ahead and put those in red one more time just to show you. That's where we're getting that. And oops, and then I'm going to show you something even cooler, because it is perhaps counterintuitive, or at least not obvious. Let's go ahead and that value was 1.6 to the negative 33. Let's go ahead and put in those values. And I'm going to pick on ESA. ESA, what do I put in for the aluminum 3 plus?
I'm not sure. Is it X?
It is X. What do I put in for the OH minus?
3X?
3X. And so let me be very clear on that. I always do that. I'm getting closer here, guys. And then of course, nope. And we're still going to cube that. Now, it turns out that when you do the solubility product, you do take into account that you are doing 2 or 3 times the amount of those ions in solution. And their influence becomes accordingly. Okay, so what does this turn out to be? I'm just going to stay in blue here. At the end of this, we end up with 27. X to the 4th equals 1.6 times 10 to the negative 33. So X is equal to?
I'm getting 2.77 times 10 to the negative 9.
2.77 times 10 to the negative 9. Anyone not know how I got 27? Or want to hear it? Kyra, tell them how.
You got 27 because 3 cubed is 27, and then x cubed is x cubed.
X cubed. Yeah.
You do 27x cubed times x is 27x to the 4th.
So then what is X?
Concentration of AG.
I was asking Kyra. I was talking to Kyra.
X is the concentration of Al3 plus and 3 OH minus.
Not quite.
Or OH minus to the 3rd power.
And 1/3 of the concentration of the OH minus.
Remember, when we get to this, 3 times the concentration of the aluminum. So when we have X, remember, we're plugging in X here, and we're plugging it in here.
Oh, that's right. Okay.
So this is a very clever distinction to make, is that when you do that, clearly the aluminum is the X. That's not a problem. But, right, oops, sorry. But when we have the equilibrium there of 3X, that means the concentration of OH minus is actually 3 times the 2.77 times 10 to the negative 9. And that is going to be 8.32 times 10 to the negative 9. So keep in mind, I always ask this over and over and over, what is X? And X is just a value. X is just what we're putting in up there. Sometimes it's glorious. Sometimes, hey, X is X is X, and it's just your stuff, right? X is the AG, X is the CL, we're done, forget about it. But you are paying attention that X is a number you put into the equilibrium value, and if you have to multiply or anything like that, you must do so. All right, let's do the last one. Stop that. Let's do the last one, and that was the calcium phosphate. So we had that Ca3, parentheses, PO42, goes back and forth to make 3 calciums and 2 phosphates, and that had a KSP equal to 8.1 times 10 to the negative 13. Let's see, who do I think is probably the shakiest? Patrick, Peter, Cottontail, you're here. Patrick, what would my KSP look like? Can you just jump to the end?
Yeah, give me 1 second. I'm thinking. It would be Ca2 plus to the 3rd, and then PO4 3 minus squared.
Does anybody need me to show them that?
Did you want the X values too, or just that for now?
Yeah, so I am going to ask you for the X values. So what would I plug in for the calcium?
So calcium would be 3x to the third. And then it would be 2x to the 2x squared.
Does anyone need me to show them that? Chef, I don't believe you.
I'm good.
You got it?
Yep.
Actually, will you do it for Celeste, please?
Will I do it for Celeste? I'll do it for Chef.
Thanks.
All right. So how did I get this? All right, so this is correct. The KSP is that, and it's equal to, let me just finish out this little drawing, and then I will show you. 8.1 times 10 to the negative 13. So we're going to come back to that. So let's do the how. Remember we had, Ca3 parentheses PO42. Go back and forth to make 3 calciums and 2 phosphates. If I did my ice table, and this is the last time I'll do this, we assume zeros. This would add 3x, and this would add 2x. So at the end, we have 3x and 2x. These values right here, if our KSP, hopefully this is okay with you, KSP is the calcium cubed and the phosphate squared. We're just going to take these 3 x's and plug them in here, and the 2 x's and plug them in there. And that's how we end up with what we have above. Three x cubed and 2x squared. Are you okay now, Celeste?
Yeah.
Chef? Okay. So now what we have to do is do this. 3x cubed and 2x squared gives us a whopping 108 x to the 5th. So we have 108 x to the 5th is equal to that 8.1 times 10 to the negative 13. X is equal to 0.00150.
Yeah.
So wow, even though it has a low KSP, you can get a measurable amount of calcium floating around in solution if you do this. Because what is X? And I'm going to go with the Chad. Oh, I didn't know. I have it right here. The X value is what gets plugged in up in here. So if that's the X value, then the concentration of the calcium is equal to 3 times X. So 0.00150. And that's usually the one we care about. We can go ahead and figure out the phosphate as well.
0.002993.
That's equal to 2x. I don't know why you get 293. Oh, because you're not rounding out a number there. Oh, Dallas. My great hanging on to everything. Okay. How you guys doing this? You guys doing okay?
Yep, we're doing pretty good.
Good. All right. So let's talk about the common ion effect. Now, this is something we actually saw in our Le Chatelier lab. Janaris, am I going too fast on these notes?
Yeah, can you scroll back up, please?
Hey, how come no one's slowing me down?
Sorry, I'm just confused because I was writing calcium.
Hey, what part of confused means you raise your hand, you shout over the mic and say, "Hey, prof, knock it off."
Okay.
For once I was actually keeping up, so I didn't say anything.
Wow.
Damn, this is like opposite day. What is this, Bizarro World? All right. Yes, Isa.
Okay, I'm good. Thanks.
What? Did I answer your question that fast?
No, it's just my mistake. I had written down something wrong.
Is
Thank
everyone
you.
okay now?
I'm good.
Are you
Actually,
guys all
I
playing
do.
Animal Crossing?
And I have a question.
I'm playing Pokemon.
All right, hold on. Who just said that?
The question,
Yeah.
Kimchi.
Kimchi, when I say, are there any more questions, why aren't you just like jumping in there and saying, I do?
Well, because I get scared. I don't know.
Wait.
So is there?
When I think of kimchi, the last thing I think of is scared. I mean, correct me if I'm wrong, Ben, but does kimchi radiate I'm scared?
No, like not at all.
Thanks,
He's
Ben.
not even here. Yeah, right? What do you think? He was saying how confident you sound. My gosh.
I just have a lot of questions. So I feel like it's annoying. I don't know.
No, what's annoying is you not asking them.
Okay.
Because I can't answer questions that aren't asked.
Yeah.
And this is some of this is not necessarily intuitive on this, so I want to make sure that we're getting what we need here. Okay, so ask away.
Okay. It's kind of similar to my last question about the solid that you started with. So there is like
Yeah.
concentration, but we just don't know what amount like you started with, right? Does that make sense? Like I know there's no initial concentration because it's a solid, but when you put it into the water or whatever, solvent, I don't know.
Solvent, yeah.
Solvent.
So I guess my question is, you have, and this may not help. Let's say you have a swimming pool,
Mhm.
and you throw a rock into the swimming pool. What's the concentration of rock in swimming pool? I guess you could say 1 rock per swimming pool. You come back 3 days later, what is the concentration of your rock in swimming pool? I guess still 1 rock, right?
Yeah.
And this kind of goes back to the idea of, and this may dovetail back to that idea of you have a pile of salt in the bottom of your glass of water. You have so much salt in there that you cannot dissolve it all, and that pile of salt still sits at the bottom.
Right.
And let's say that you were just taking your big ass Morton salt container and you're just pouring it. You might imagine that you'd make a cone at the bottom of your glass of water, just like you'd make a cone on dry land. Yes?
Mm-hmm.
Okay. And you leave it, you just let it sit for like 3 days, and that cone is still there.
Mm-hmm.
Now, let's say that you flatten out that cone. Let's say you get in there and you stir it up and you let everything settle all nice and perfectly flat on the bottom. Did you change how much salt could go into solution?
No.
No, it was already saturated, right?
Yeah.
Now, the reason why I sort of bring that up, and I don't know if this will dovetail well, is when we are trying to figure out how much salt is in the water, how much salt dissolved into the water, why do I not care whether or not the solid salt were shaped like a cone, shaped like a rectangle, made to look like a unicorn? Why don't I care about that solid chunk that is sitting there?
Because
it doesn't matter.
It doesn't.
That's not what we're trying to measure. Are you
Okay.
measuring the concentration of conical salt versus rectangular salt in your solution, or are you measuring the number of ions that are floating around in solution.
The number of ions.
Right. And that's why we don't care about the concentration of that thing.
Right. Okay.
We only care about what it is going to give off.
Okay. I guess that was kind of a bad question because there's not like a final concentration, but there's a final amount of solid. So I think I was just asking, like, can you find that with what you have?
Could you, well, I guess if you really wanted to find the final amount, yes, you could. You could say, oh, I have this, you know, I don't know, chunk of marble. Now, you know, if you were here with me with Chem 110, I have this demo where I throw a chunk of marble into water and I shake it up and I say, is this soluble or insoluble? And everyone goes, it's insoluble because the rock is still sitting there. There's nothing going away. We don't see anything. You and I have just proven that some will go into solution.
Mm-hmm.
How much? I don't know. 1/1,000,000th of a mole's worth, sure. Sure, nothing is insoluble. There's always going to be something that can dissolve. Whether or not it's measurable, detectable, or the like is another question. But sure, you could take that chunk of calcium carbonate, that marble. You could drop it into the water. You could come back the next day and find out that you had 10 to the minus 7 moles of that marble gone away. You could convert that moles into the grams of the calcium carbonate and find that you had like 10 to the minus 7 grams taken off of your 18-gram chunk of marble.
Mm-hmm.
What did that do to the total amount of your marble? Nothing.
Yeah.
So you could do the absolute amount that came into solution, but there's really no point, is what I'm coming down to.
Yeah. Okay.
But hopefully that actually answered your curious question.
Yeah.
Meanwhile, Alfredo's going, moving along, please. I'm just, yes?
So
Hey, who's
I
that?
had a bit of a question. This is Dallas.
Oh dear, yes?
So why are atomic coefficient things, why are they factoring into our calculation like 3 separate times?
Because, moving on. It just is. I don't know that I can give you a physical reason why, except for it probably ends up coming into the activity of those ions in the solution, which is something I don't want to go into. And also, I'm just sort of conjecturing there. Basically, at a certain point, it is the math that works for what we physically observe in the real world.
All right.
AKA magic. Leave me alone, Dallas. You know I love you, man. All right, let's talk about this. The common ion effect. Let's talk about this common ion effect. Ooh. Let's go back to the one lab we were actually able to do before we couldn't do anything. Let's do some silver chloride with HCl. And I'm going to be specific, 0.2 molar HCl. I want to see what happens if I toss something in there that actually gives us a piece of the equation. I just want to point out that if we look at our pieces, what are our pieces when I dump these two things into solution? And I'm going to go with, oh, I already called on you, Alexia. Hey, Alfredo, you didn't answer me last time, so you're on deck now. Alfredo, what are our pieces when I dump these two things together? Oh, wait, he's not on my list of people that will talk to me. Sorry about that. Boudica, I haven't got you for a minute. Boudica, what are our pieces?
AG and H.
AG and H. Ooh. I'm nervous about accepting that. Help her out. Ben, what do we got?
AG and C.
Almost. We have AgCl and Cl. If you remember back to that lab, we actually said, hey, how come adding hydrochloric acid didn't dissolve silver chloride, but it would dissolve the silver acetate, right? That was essentially a common ion effect insofar as we were using another equilibrium to help out. But if we look here, our two ingredients are actually silver chloride and the chloride. So we have AgCl back and forth to make Ag plus and Cl minus. Now, if we were to set up an ice table like we normally do, once again, for Chem Chi, the AgCl just doesn't matter. Given our situation that we have right here, above, this here right here, what are our initial concentrations of Ags and Cls? I'm going to go with Celeste.
Can you repeat that?
What are our initial concentrations of Ag and Cl given the situation that we see right up here?
Is it the same as the others? Nothing?
Almost. Gonzalez, what do you think? Oh, wait, he's not on my list of people who talk.
She's correct for the Ag, but for the Cl minus, it's 0.2.
That is correct. You see, when I start dumping in something that brings in a piece of the puzzle, we are assuming that we get to have that there. Okay? So this 0.2 here comes down as part of our initial dumping ins. Now, if we dump in some more CLs, let's go back to the things that we are a little more comfortable with. If we dump in more chlorines on the right, what is going to happen to the equilibrium?
It's going to shift to the left.
It's going to shift to the left. We are going to now mathematically show this common ion effect and actually quantify that. So for the rest of this, we should be able to note, and I'm going to go ahead and put that 0.2 here in that golden stuff. We should note that this will still give us a plus X and a plus X. So we have X and 0.2 plus X. If we solve this, we have X times 0.2 plus X is equal to this 1.8 times 10 to the minus 10.
Is that your KSP?
Oh yeah, that was our KSP. What, you guys don't have that in your notes sitting right next to you so you can just read it off?
Nor can I read your brain or read your mind.
Oh man, I'm trying to work on my projection of that. Hey, if we go ahead and solve that for X, we find that X is equal to 9 times 10 to the minus 10.
Yeah.
Which of course is that concentration of the silver. Now, that would also mean though, that the concentration of chloride is equal to 0.2 minus that 9 times 10 to the minus 10, which means that it still looks like it's 0.2. But the one we really care about here is this silver. So when we talk about the solubility, we're almost exclusively talking about that metal that we're in there for, because those are the ones we care about trying to get rid of. So this isn't anything new to us. We know that if we loaded up the products, we should shift to the reactants.
Fourth, it's plus for the Cl minus. Like
oh, sorry. Yep, thank you. We knew the concentration would go down. Because of Le Chatelier. Now all we're doing is quantifying it. And if you note, without the common ion effect, without the Cl minus, the common ion. So between the two of these, the Ag going to be Ag plus and Cl minus, the HCl has the same sort of thing since they both have that chlorine in common. We call that the common ion. Without the Cl minus, the concentration of Ag plus was 1.34 times 10 to the minus 5. By adding the Cl minus, we've drastically reduced its concentration. By adding the Cl minus, we drastically reduced the concentration of silver ions. So one of the ways to get things out of solution is to just dump something else in there that'll suck them out. It's a common way of getting things to drop out of solution, and we did a lab on this where we went through, we dumped in something that was going to bind up with it. In your case, it was I believe hydrochloric acid as well, and it took that silver chloride out of solution. It might have been salt water. I can't remember now. But with that, we can see that it's a combination of the Le Chatelier in there, but now we actually get to quantify what is going on.
And then you just have to pull out the Ag plus from the hydrochloric acid that you just dumped in there.
Sure. So what? Who cares? Remember, chemists and chemical engineers, our whole job is to fix the world by screwing it up and screw it back up to fix it again. That's what we do. That's what we do. You got a problem, we'll fix it. Oh, we made a new one? Oh, we'll fix that one too. Okay. Ooh. Check this out. Let's recall something else. Ooh. Recall that we had that aluminum hydroxide back and forth to make Al3 plus and 3 OH minuses. And we had that KSP equals to 1.6 times 10 to the negative 33. We did this before. So we're just recalling this. At the end of everything, at the end of it all, we found that the concentration of the aluminum 3 plus was equal to 2.77 times 10 to the negative 9. We were wrong. It is 1.6 to the negative 12. My question is, why? And to answer that question, I'm going to pick on, oh, who's been talking a lot lately? Or who hasn't? Oh, the Wonder Twins. Ashley and Aiden, why? Why were we wrong? Oh, I guess they're busy not answering.
Because there were already hydroxides in the water.
Or there's
Yes,
hydrogen.
that is correct. There were already hydroxides in the water. So how does that affect things? Well, if you have H2O going back and forth to make H plus and OH minus, and let's just remind ourselves that the Kw is equal to 1 times 10 to the minus 14. That means that the concentration of H plus is equal to the concentration of OH minus, which is 1 times 10 to the minus 7. You can solve that as x squared equals 1 times 10 to the minus 14. X is equal to 1 to the negative 7. And that is now the H plus and the OH minus concentrations. Which means what we have to do is go back to our original here, aluminum hydroxide, back and forth to make Al3 pluses and 3 OH minuses. When we do our ice table, while our aluminum hydroxides we don't care about, we now actually do have an initial concentration of hydroxide. Those are a common ion for the aluminum hydroxide case. So the aluminum itself started out at 0, but the hydroxide started at 1 times 10 to the minus 7. And then, of course, we just add 1x for the aluminum and 3 x's for the aluminum hydroxide. And so you end up with x and 1 times 10 to the minus 7 plus 3x. Is everyone with me?
Yep.
Yep.
Okay. Meng, are you with me still? Uh-oh. Somebody abducted Meng. All right. Everyone note the time so we can tell the police when we file a report.
It was 11 a.m.
Thank you. Wait, that would not be funny if that were real. So let's not laugh, just in case. All right. Remember the KSP is equal to the concentration of aluminum 3 plus n times the concentration of OH minus cubed, right? Because we have 3 of them. Everyone's okay. So this is now x times 1 times 10 to the minus 7 plus 3x now cubed.
And now we all pray that we can neglect X.
Well, considering that KSP was 1.64 times 10 to the negative 33, what do you think? Can we neglect X?
Yeah.
Yep. And so now we have X times 1 times 10 to the minus 21 is equal to 1.6 times 10 to the negative 33. So X is equal to 1.6 times 10 to the negative 12.
Yep.
Which we just said was the concentration of aluminum 3 plus. QED.
Hey, question. So this would be very similar if there was an H plus involved instead of an OH minus.
Say that again, Chef.
So like, right, we're starting with 1 times, or 1 times 10 to the negative 7, but it would be very similar if it was an H plus.
Well, the H plus would not be a common ion here.
Okay.
So no.
Okay. If we were,
I think she's asking if we had an ion, if our initial thing involved H's instead of OH's.
Yes. Yes. So let's say we're an acetic acid solution and you decided to put in some other thing that had H's. Yes, you would add those in because HAC breaks up into H plus and AC minuses. You absolutely would add those in as your initial. Keep in mind, this is very, very similar to when we said, hey, we're going to dump in ingredient A, B, and C. What are the equilibrium concentrations? And sometimes we had to shift it and things like that. This is very, very similar to that insofar as you're now taking, instead of a solution plus solution, you're taking some sort of solid that has an equilibrium and adding one of its products or more, but at least one of its products to sort of mess up what that equilibrium would be, and then control the solubility that way. And so oftentimes water is not going to be an issue here. I mean, if we go back to this AgCl with the H pluses, with the hydrochloric acid, we aren't going to worry about any of those H pluses. They don't show up in the splitting apart of AgCl. It's only the chloride that we actually care about. So the H's are just bringing the chlorides to the show. But if you do happen to have something that shows up there that is found in your water, you want to be careful about that.
Now, what does QED stand for?
What are you yelling at me, Kyra?
What does QED stand for?
It has been proven.
Oh, okay.
I just proved our 10 to the negative 12 from before.
Okay.
I'm sorry, how does QED stand for
Latin.
it has been proven?
It has been proven, it has been shown. Look up QED on your Google right now. Latin, QED. I forget what it's called. I've looked it up several times. So while he does that, to come back and say it's something demonstrated, demonstromo, I think is what it comes out in Latin, I forget. The rest of us will move on and he'll catch up.
Quod erat demonstridum, which loosely translated means that which has to be that which was to be demonstrated.
That which was to be demonstrated, and I just demonstrated it. Therefore, QED. All right, let's control solubility by pH. So you can use a common ion, and I introduced that before I do the pH because I need you to see that the that the concentration of H pluses will roundaboutly, as it were, become a common ion in other systems. So if we look back up here, we had systems where we weren't caring about the pH. What we were doing instead was bringing in some other ion that was part of the equation, whether it just happened to be the chloride there, or maybe some background radiation of hydroxides in the first place, because that was part of the system. Now what we're going to do is show that sometimes the pH will control something else, which will control the solubility. So it will essentially, one person removed, become a common ion. So let's talk about some pH-controlled solubility. So what I'm going to look at is silver sulfide with hydrogen sulfide. Now, each one of these will set up an equilibrium. You'll have your silver sulfide breaking apart to give you a couple of Ag pluses. and a sulfide 2 minus, and that has a KSP equal to 6.62 times 10 to the minus 10, or sorry, 50. Sulfides are not very soluble, guys. Sulfur, once it gets a hold of you, does not like to let go. But hydrogen sulfide will also set up its equilibriums. Now, since it's a diprotic, the first one will be H plus HS minus, and that has a Ka1 equal to 9.1 times 10 to the minus 8. It'll also do HS minus back and forth to make H pluses and S2 minuses, and that has a Ka2 equal to 1.0 times 10 to the minus 12. And here's where it gets kind of interesting, because this right here has to be aqueous in the first place. So how do we get hydrogen sulfide to be aqueous in the first place? Well, we take hydrogen sulfide gas plus water and get wet. This, by the way, happens to have a K equilibrium of 0.1, which means it goes back and forth pretty easily. Now, as we write these down, I hope you can see how this thread is going to go through. What I'm going to do is I'm going to take some hydrogen sulfide gas, which will turn into H2S. That H2S will slowly turn into HS and HS, and finally sulfur 2 minus, which is right up there with our silver sulfide. So we have a lot of systems here that are going to become into play, but at the end of it, all wrapped up in the middle of this, sneaking its way around, are some H pluses. And that's where the pH is going to come into play for controlling the solubility. So what we're going to do is we're going to bubble some H2S over and over and over through water until it finally reaches its equilibrium. So we're going to bubble H2S gas through water until equilibrium is established. Now, it doesn't take very long, because once you actually do that, you'll find that you make a constant steady stream of H2S. This will give a steady stream of H2S AQ, which means it'll give us a in solution. I'm going to do this for you mathematically, because once, and let me just be very clear, once I can do, that is out of this, I'm getting all excited. For someone who's trying to clean up their handwriting, I'm not. So if I basically have a constant stream of H2S coming through there, H2S gas, it will give us a constant amount of hydrosulfuric acid. If I have a constant supply of hydrosulfuric acid, that means if this is constantly being regenerated, then that is constantly being regenerated. But I can shift that. And I can shift that by controlling the H's now. And we're going to watch this mathematically, how it gets really, really cool.
Before we do that, quick thing. So when we're doing that, the initial equilibrium between the hydrogen sulfide gas and aqueous.
You mean this guy? H2S gas plus good old-fashioned H2O liquid goes back and forth to give us hydrosulfuric acid, right?
Yeah. So we put pump some amount of the gas into the water, and some of it like dissolves into the water, and like the rest sits as a bubble at the bottom of the container.
No, I mean so unfortunately we did not do the carbonic acid lab for you to have this familiarity. If you had done that lab, you would have taken some sulfuric acid and some baking soda, you would have reacted them, you'd made carbon dioxide gas, and you would pump that carbon dioxide gas through water. And so you just see the CO2 just blub, 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 blub through the liquid, okay? These bubbles don't just sit anywhere, they're just continually flowing through and going out the top. And so any excess that's not absorbed is just wasted out the top, who cares? But if I were to write this, go ahead.
But so if it is escaping out the top, then that means that the left side is going down, in which case.
No, because I'm constantly giving it.
Oh, so you're pumping in more as we go.
That's right. It is a steady stream.
Okay.
Yeah. So I just want to point out that since this is a gas, we should put the pressure of the hydrogen sulfide down there. And I'm going to go ahead and put this here real quick, just so we keep it here. If we were to write the KEQ for this reaction, this is what we would nominally do. Of course, you guys would say get rid of the water because it's a liquid, right? Because it's a liquid, get rid of it. And here's what I'm going to do. Dallas, if I am blowing hydrogen sulfide gas, just bubbling through like you taking a straw and bubbling through your soda when you're a kid, what is the pressure of that hydrogen sulfide gas? Ooh, let's set a little Chem 120 action on us. I'm going to ask Tristan, what is that pressure? I will give you one guess.
What the pressure of the H2S?
Yes, I will give you one guess.
Is it going to be like the standard?
One chance. Meng, he has one chance. Help him out.
Are you saying one chance because it's just going to be one?
That's right.
Yeah.
Specifically one what?
Is it going to be atmospheres?
That's right. So, since we are bubbling, at atmospheric pressure, the pressure of H2S is 1 atmosphere. You're just blowing a stream of air in 1 atmosphere's worth of stuff. You aren't pressurizing the system, and in order to push air through, you have to at least have that pressure. So guess what?
Wait, but how do we know that the pressure in the water is the same as the atmospheric pressure? I mean, the water at the bottom of the ocean is way higher.
It is. No, it's not. You go to the bottom of the ocean. That's different. I'm talking about bench top right here, Dallas. Pressure is going to be 1 atmosphere. So since the concentration of water doesn't matter and the H2S is 1, guess what this means? This means that the KEQ is equal to the concentration of H2S, which means it is 0.1. If we are making a steady stream of gas through our liquid to keep that aqueous solution going, its value will be the equilibrium constant. So really the value of that is just a number. So let's go back to that H2S. We had H2S goes back and forth to make H plus and HS minus with a Ka1. And we had HS minus goes back and forth to make H plus and S2 minus, and that has a Ka2. If we add those two up, what do we get? We have H2S makes two H pluses and an S2 minus with a value of Ka1, Ka2. Nothing new, nothing exciting. We've done this. But we can write the equilibrium expression for this now. And that would be the Ka1, Ka2. Oh, I saw bodies outside my window. It scared me. Just my wife and kid. Is equal to the concentration of H plus squared times the concentration of S2 minus all over the concentration of H2S. What if we solve this for S2 minus? We'll get S2 minus is equal to Ka1, Ka2 times the concentration of H2S all over the concentration of H plus squared. Now, this is where it gets kind of cool. Because if you look at this, everything up here is just a number. Ka1 and Ka2 were just values, and we just proved that H2S was 0.1. It's just a number. You guys with me? That's not a variable.
Yep.
So let's remember, we had that Ag2S goes back and forth to make a couple of Ag pluses and an S2 minus. And its KSP was equal to the concentration of Ag plus times the concentration of S2 minus. Well, don't we have an expression for S2 minus?
Yes.
We absolutely do. So that means that the KSP, well, actually, let me solve this real quick for our silver ion concentration, because that's what we actually care about. So the concentration of Ag plus is equal to the KSP divided by the concentration of S2 minus. You remember when I said it's just math, guys? Check it out. Let me see if I can remember this. Okay. So this is going to be KSP times the concentration of H plus squared all over Ka1, Ka2 times the concentration of H2S.
Wouldn't the KSP be AG squared?
I'm sorry?
Like the AG plus, isn't it squared? Because
I couldn't hear that. I'm trying to process that. Say it again louder, Kimchi.
the AG plus, like when you write it with the KSP equation, isn't it squared because there's two?
Oh, sorry. Yes, I was thinking. I was back in my AGCL. So let me go back to the top. You're right. It should be two AG pluses and an S minus. I don't know what I was doing there. So it should be squared. So at the end of this, the concentration of Ag plus is equal to all of this, KSP times the H plus squared all over Ka1, Ka2, concentration of H2S. Take the root. And I want to point out here that everything here in our nice little rainbow bubble is just a number. And we can actually calculate what that number is. I'm going to go ahead and put it out here, and then so our KSP was what, 6.62 times 10 to the minus 50. I'm going to take our Ka1, which was 9.1 times 10 to the minus 8. Our Ka2 of 1.0 times 10 to the minus 12. And our H2S of 0.1. That is all to the 1/2. And now times H plus. And it's not squared anymore because I took the square root of it.
I'm getting 2.69717 times 10 to the negative 15 times the concentration of H plus.
Slow down again.
2.69717 times 10 to the negative 15 times the concentration of H plus.
2.697 times 10 to the negative
15.
times 10 to the negative 15.
Yeah.
Times the concentration of H plus. And this is equal to the concentration of the silver ions. Now, what does this mean? This means
pH is going to be a scaling factor to the Ag plus.
Yes. This means that the concentration of silver is now dependent on the concentration of H plus. What we've done there is we have now successfully shown that if we choose the right system, and this works very prominently with sulfides and carbonates, very easy to control their amounts. And I'll show you a carbonate one when we come back from break. But if we look at this, and let's go ahead and, ooh, we have Excel. Dallas, keep track of that. So let's get Excel going on here.
Keep track of the fact that we have Excel?
No. Everyone else understood what I meant. I need the numbers. Stay there. Okay, good. So here I'm going to have Ag plus. And over here, I'm going to have pH. Now we said that the concentration of Ag plus was equal to, Dallas, if you can give me that number again,
2.697
697
times
Where's my
10
times
to the
10
negative 15.
times 10 to the negative 15 times, and I need to get B2. Let's see if that did something. Nope. I need that as an exponential, but I don't think I have. I don't have the I don't have the scientific calculator for this. Hold on. I can do this. There we go. So if I take this, where's my mouse? Mouse would be better. If I take this now and I fill it down a little bit, and I have a pH equals 1, so if I go pH here, this will actually be H plus concentration. I apologize. Well, why am I apologizing? I'm doing an Excel spreadsheet for you, just like you guys wanted. So my pH is 1, 2, 3, 4, 5, 6, 7, 8. Let's do it like that. This is going to be equal to
10 to the negative the 1 over.
I can't get a caret, can I? Well, shoot, I can't type it in like that. So that's going to be 0.1, and this will be 0.01, 0.001, and so forth. If we drag it down, why didn't you drag down the 0.1? Shoot. 0.1, 0.01, 0.001. Let's try that again. What?
Yeah, Excel doesn't always understand things that aren't equations.
That was weird. It should have like. So hopefully you guys can see here that as we get further along here, you could actually plot this, and you could see that we are getting less and less soluble as we get more basic. We're going from 10 to the negative 16 to 10 to the negative 21, and you could actually plot this out and watch that solubility drop off accordingly. It was an exercise that went nowhere. So I apologize for that. But anyway, so what you do is you control the pH. You control the pH using buffers. This controls the H plus concentration. This controls the concentration of the silver. So as we look at that, we can control how much silver goes into solution by just making a buffer solution, given the fact that we can control the hydrogen sulfide that we're generating. And again, this has ramifications down into wastewater treatment as well as a few other things. Okay. I have a feeling that it's later than I thought. What time is it? 11:30. I think brains are probably full here. Is that correct?
Yes.
Yep.
Yep. All right. So why don't I go ahead and end this recording here, and I will. Let's see. Stop the recording.